Hello, welcome to 5th International Symposium on Multidisciplinary Studies and Innovative Technologies. Due to COVID-19, we are organizing the symposium virtually. I hope this epidemic will end as soon as possible. Let's start the sessions if you want. First paper belongs to Mr. Ali Karaca. Are you ready to present, Mr. Ali Karaca?
Yes, I'm here.
Okay, you can start if you are ready.
Thank you.
You have 10 minutes, please.
Okay. Good morning, everyone. I'm Alican Karaca from Yıldız Technical University. The title of my presentation is Robust and Fast Shift Detection in SAR images with complex backgrounds based on efficient data model. Let's begin by explaining what synthetic aperture radar is. Synthetic aperture radar is an active remote sensing system that transmits polarized signals and measures echoes frequently. The most two important properties of this imaging technique is resolution. It can produce high resolution data at any time of the day, and it is independent of weather conditions. You can see some applications of SAR imaging technique here, and especially ship detection has gained a great attention for maritime traffic monitoring in the last decade. In literature, ship detection research can be grouped into two parts: conventional methods and deep learning methods. And conventional methods, have some disadvantages: high computational complexity, generalization problem, and determination of suitable ship features are three important disadvantages in conventional methods. To address these problems, many deep learning methods have been developed, but there are still some challenging problems. For example, the ships can have different size. The ship's size can be small, large, or medium, as is seen in figure. Or the SAR image may have complex backgrounds, as is seen here and here. It's a problem, and a robust classifier should find out all these ships accurately. We want to find the ships as short as possible, and fast detection is another important topic for us. So in this paper, we proposed the usage of efficient data model to provide a fast and robust solution to the aforementioned three problems. Efficient data has lots of advantages, but two of them high object detection performances, and it can be implemented to an edge device with fast detection times. Here is the architecture of efficient data model. First, the image is applied to efficient net B0 backbone pyramidal network, and it will provide multi-scale features from P3 to P7 layers. These outputs are applied to BFPN networks. BFPN network has top-down, bottom-up connections and other connections. Each node inside BFPN layer takes 2 or 3 inputs and fuses them by weighting the inputs. And also, finally, to obtain the box and class parameters, the outputs are applied to these networks. SAR ship detection dataset was used in our experiments, which can be found in reference 1 and reference 7. These datasets includes nearly 40,000 ship chips or ship patches, and these images are obtained from GoFan3 and Sentinel-1 satellites. During the experiments, we randomly split the image of the dataset into 70% of training dataset, and the rest of the dataset is used in the test stage. You can see number of training and test samples in terms of different satellites. We compared the efficient DAT model with faster RCNN, RetinaNet, and SSD MobileNet models, and the implementation of all methods were realized on TensorFlow 2 and using Colab, Google Colab. Also, the parameters of the different models can be seen here. The detailed parameters are shown in here. I will not explain all these equations and metrics due to time limits, but in this research, 13 evaluation metrics were used, which are also known as Pascal-Vogt and COCO metrics. And note that average precision here measures how many ships are correctly localized, whereas average recall scores are related to how many ships the detector can find out. Let's take a look at precision recall curves. If you look at the area under these curves, the highest area is obtained by efficient DAT model, which is colored by blue, and the lowest one is obtained by SSD MobileNet, which is colored by black. As you may know, MAP metric is calculated over the area under curves, and MAP score shows the same information as previously mentioned. Evaluation metrics for different models are shared in this table, and in general, efficient DAT D0 model achieves the best performances as it obtains highest value 9 of 13 metrics. You can see both the highest metrics in the table. The highest AP score is also obtained by efficient DAT model. According to AP 75 result, the model gives at least 9% higher values, which shows higher localization property under complex backgrounds. Moreover, average precision scores of small and medium ships are also found more correctly by this model. Let's see some visuals about the detection results. Each color of bounding boxes show a specific method and the ground truth. As is seen, the images have complex backgrounds which may cause false alarms. For example, SST here, SST MobileNet detects more number of ships compared to ground truth, and it has false alarms. On the other hand, RetinaNet may miss some ships, some small ships. For example, RetinaNet is not detected this ship here. If you look at different results, faster RCNN correctly finds the small shapes and medium shapes, but it is not robust to complex backgrounds, and also finds many shapes that are not originally shaped. If you look at the performance and detection times together, we compare MAP score with test time per image together, and the method in the top left here, efficient data model. So it has lowest test time and highest MAP score in the top left. In summary, we observe that it also provides a fast detection, not only gives the best detection performances, but also provides a fast detection. In conclusion, we propose the usage of efficient data model for fast and robust chip detection, and efficient experiments demonstrate that it provides the best performances among the other methods in terms of Pascal walk and Cocoa metrics, computational times, and visual comparison. Here are the references of the work, and thanks for your attention.
Thank you for your presentation. Dear participants, do you have any question about this article? Okay, no question. Thank you again. I wish you success.
Thank you.
Next paper belongs to Alvalet, dear Alvalet Taha. Is online. Okay. Dear Elham Pashai, are you ready to present? Yes. Okay, yes, you can start if you are ready.
Yes, I can.
Okay. You have 10 minutes, please.
Okay, thank you. Wait. Wait a moment. Sorry, I cannot stop the sharing. I want again.
Okay.
Wait a moment. Wait. Sorry again. Okay, my name is Elham Pashai, and the title of my paper is Medical Image Enhancement Using Guided Filtering and Chaotic Interior-Weight Black Hole Algorithm. So first of all, at the first, we have an introduction, then I explain about the objective of this paper and explain about the application of the image enhancement. Then I explain about the purpose method. We have experimental result, and at the last, conclusion. So in introduction, first of all, I explain about the image enhancement. So image enhancement is basically the method of manipulating or improving an image where the visual appearance of the output image is more compatible than the original image for a specific or dynamic application. So at image enhancement technique, we have two approaches. One of them is a spatial domain enhancement, another one is a frequency domain enhancement. So at the spatial domain, we deal with the image plane itself, whereas at the frequency domain, we deal with the rate of the pixel change. So the spatial domain works based on the direct manipulating of the pixel, whereas frequency domain work based on the modifying Fourier transform. So here in our approach, we work based on the spatial domain enhancement. So now I want to explain about the chaotic intervariable black hole algorithm. So black hole algorithm is the evolutionary algorithm that the solution in black hole algorithm are called stars. So in the evolutionary algorithm, you know that every solution created randomly and put within the search space at the beginning. So the algorithm works based on the randomly created stars and then look for the best star, which is called the black hole, and it works based on the fitness function. After indicating the candidate black hole, stars begin to travel around it, and the black hole absorbs the star that falling into it did that. So during the process of the searching for the optimal solution, if a star reaches a better location while moving toward the black hole, the position of the black hole is changed within the star's position, and the search will continue. Moreover, if the certain boundary around the black hole known as the event horizon is crossed by a star during the movement, the black hole expels the star, which leads to birth of a new star randomly. So now I want to explain about the chaos. Chaos is a schema that has three critical characteristics. One of them is a godicity, stochasticity, and sensitivity to the initial condition. The combination of these properties guarantee the diversity of the solution and therefore improve the performance of the evolutionary algorithms. So what is the interior weight? Interior weight is a coefficient that controls the balance between exploration and exploitation. Chaotic interior weight is exploited to efficiently control the convergence of the best global solution. So what is a guided filter? Guided filter is a technique that preserves age and details of the image while removing noise and also avoid straight case and gradient reversal artifacts of the resulting image. To smooth the input image, the guided filter use the content of the input image and a guidance image, in which the guidance image can be either another image or the input image itself. So the principal benefit of the guided filter is to retain the image information throughout the filtering process. So the main object of this paper is to make an image more suitable than the original image in order to, the second aim is to enhance the contrast, which keep the natural looking of the image, and this helps to make the image suitable for dynamic fields. So if I want to explain about the application of the image enhancement, we can say that image enhancement can be used in the medical sector, in a remote sensing application, and in document image. So here in this paper, we use it for the medical problems. So now I want to explain about the purpose approach. At the first, we have an input image. Then after that, we use a guided filter. In fact, we apply the edge perception smoothing filtering method by using the guided filter. Then we have a smooth output, and in this smooth output, we apply the chaotic weighted black hole algorithms by using a new fitness function that we propose, and then we reach to enhanced image. So here, this is our fitness function that we propose it. Our purpose fitness function is the combination of the two fitness functions, fitness function 1 and fitness function 2. At the fitness function 1, as you can see here, we reach with this formula. So in this formula, IE denotes the obtained image after transformation. ISE is a resulting image after performing the Subel age detection operator to enhance to obtain image, and the EISE is the sum of the H pixel value. So the NEIE show the content of the each pixel in the enhanced image, and HIE is the entropy of the image. So the fitness function, the second fitness function is Q multiplied with 0.5 multiplied with the entropy power log to n, and EISE multiplied with the contrast. So the Q, N, and C one by one. Q indicate the universal image quality index, N indicate the GLCM based energy, and C indicate the GLCM based contrast. So now I want to explain about the experimental results. So as experimental result, first of all, for the one medical image, we compare the performance of the fitness function and compare the performance of our proposed approach or proposed fitness function with two other state of the fitness function. So the first fitness function is the two-box fitness function, which use the age information, entropy, and texture features. And the second one is a convolutional fitness function based on the age pixel intensity value and entropy. And we compare the performance of them with six evaluation metrics: contrast, H pixel, entropy, PCNR, SSM, and MSE. As you can see in most of the these metrics, our proposed method reached to better results. Our proposed fitness function. So the experimental result, medical one, at the medical one, as you can see in this result, we show the enhancement result of the image with a 10 approaches, different approaches. So first one is the input image, and one by one. Second one is a particle swarm optimization. Third one is a histogram equalization, contrast limit adaptive histogram equalization, different methods such as screen-posing equation. And also we draw their histograms. As you can see, the result, the last result is our proposed approach, which show, when you pay attention to the histogram equalization, it can follow the shape of the original image, and it's a flatter. So it shows good performance. For the second image, medical image, also we compare the performance of the different approaches and draw the histogram of that. Also the result is better compared to other approach. And the third one is the mammography image, and here also we can see the better performance compared to others. Now we compared the performance of a proposed approach based on the entropy and PCNR. And as you can see, our proposed approach reached to better result in terms of the PCNR. We reached to a better result compared to other approaches. In terms of the entropy, we placed at the second highest. And now, at the conclusion, in this study, a new hybrid approach is suggested for medical image enhancement. The main idea is based on the hybrid of the guided filter and chaotic intervariate black hole algorithm to enhance the highlight the image information using a new objective function. So, in the purpose objective function, we consider the universal image quality index, entropy, H pixel, and gray level cocurrence matrix based contrast and energy are considered. Then the experimental results are verified a medical image by comparison with the well-known image enhancement technique using entropy and peak signal to noise ratio measurement, and the extensive experiment along with qualitative and quantitative evaluation show that the suggested method can successfully enhance image and perform better than the most state-of-the-art techniques. So as a future work, we can say that the usefulness of the proposed method can be investigated in solving other related domains of image processing, such as segmentation and noise reduction. Thank you. Thank you. Any question?
Okay, I missed my voice.
Okay, now I
Okay,
hear.
thank you again.
Thank
I wish you success. Dear participant, do you have any question about this article? Okay, no question. Mr. Günektar, do you have any question?
Okay, actually we didn't see the presentation and I don't have any idea about the presentation, so
Okay.
I don't have any question. Thank you.
Okay.
What?
We didn't the presentation on the screen you shared, and we don't have any idea about what you done.
But I shared it with you.
Oh, maybe it's a problem for me.
Dear Ernest Pasha tried, but it cannot be seen.
Yes, I am here and I share my presentation. Now you can see it or not?
Third presentation.
No, we didn't see.
Again, you didn't see.
Yeah.
So can I present it at the last of the everybody again?
No.
No, it's not problem. You try twice. You tried twice, but it's not seen.
Yeah, we just informed. We just informed you. Okay.
Thank you.
Thank you.
Thank you.
The last paper, next paper is convolution neural network method used in computer vision belong to Ferit Can.
Yes, sir. It's me. Can you hear me?
Can, are you ready to present?
Yes, I am ready. Can you hear me?
Yes.
1 minute, sir. I will
You can
share
start
my
your
screen.
presentation.
I think now you can see the presentation, I think.
Yes.
Good morning, sir. Good morning, all. I am Ferit Can from National Defense University. My subject is convolutional neural network architectures used in computer vision. Because we prepared our study in Turkish, from this time on, I will continue my presentation in Turkish. I am sorry for the ones who doesn't speak Turkish. Sunumun içeriği yansıda görülmektedir. Öncelikle kısa bir giriş yaptıktan sonra yaygın olarak kullanılan CNN mimarilerine değineceğim. Karşılaştırılması, literatür taraması, incelenen çalışmaların karşılaştırması ve sonuç. 10 dakikada bitirmeye çalışacağım için biraz hızlı geçeceğim. Bilgisayarla görü bildiğiniz üzere görüntünün bilgisayar vasıtasıyla işlenmesi, öz nitelik çıkarımı ve sınıflandırma neticesinde görüntü içerisinde yer alan nesneleri tanıma yeteneği olarak tanımlanabilir. Görüntü verisinin miktarı özellikle akıllı telefon, güvenlik kamera ve uzaktan algılama gibi sistemlerin yaygınlaşmasıyla birlikte önemli ölçüde artmıştır. Artan görüntü verilerini kendi kendine işleyen, sınıflandırılabilen yazılımlara ihtiyaç önemli ölçüde artmıştır. Bilgisayarlar görü genel olarak nesneleri tanıma yeteneği olarak tanımlanabilir. Yansıda görüntü sınıflandırma bilgisayarla görünün ana hedefi olmakla birlikte bunu zorlaştıran bazı faktörler bulunmaktadır. Bunlar yansıda belirtilmiştir. Bakış açısı değişimi, aydınlatma koşulları, deformasyon, üst üste gelme, nesne ve arka plan ilişkisi, sınıf içi farklılıklar. Bilgisayarla görünün amacı da bu görüntüleri yorumlayacak ve bu bahsettiğimiz zorlukların üstesinden gelecek bilgisayar programları yazmaktır. Yine bu bölümde tasarlanan ilk CNN mimarisinden günümüze kadar olan süreçte sıklıkla kullanılan CNN mimarilerinden bahsedeceğim. Konuyla ilgili yapılan ilk çalışmalar 90'lı yıllara dayanmaktadır. Hepinizin bildiği üzere Lekun ve arkadaşları 98 yılında el yazısı karakterleri sınıflandırmak için yansıda görülen CNN mimarisini oluşturmuştur. Burada dikkat edilmesi gereken nokta, sistemin geliştirildiği dönemde mevcut işlemci gücünün düşük, grafik işlemci birimi, GPU yeteneğinin yani paralel programlamanın gelişmemiş ve ayrıca eğitim maksadıyla kullanılan veri kümelerinin nitelik ve inceliğinin yetersiz olması söz konusu mimarinin geliştirilmesinde yönelik engeller olarak sıralanabilir. Yine bir dönüm noktası Alex ve arkadaşlarının 2012 yılında yüksek kapasiteli CNN mimarisini ImageNet yarışmasında kullanması ve rakiplerine önemli ölçüde bir üstünlük sağlayarak birinci olmasıdır. Yansıdaki mimariyi görmektesiniz. VGGNet yine AlexNet mimarisinden hemen sonra 2014 yılında geliştirildi. VGGNet ve GoogleNet, AlexNet mimarisi hata oranını önemli ölçüde azalttıkları görülmektedir. VGGNet %7.3, GoogleNet 6.7 başarım yakaladı ImageNet yarışmasında. Yine VGGNet, AlexNet mimarisinin geliştirilmiş bir versiyonudur diyebiliriz. AlexNet mimarisiyle arasındaki farklar incelendiğinde öncelikle katman sayılarının arttığı görülmektedir. 2012 ve 2013 yıllarında 8 adet katman sayısı VGGNet mimarisiyle 19 katmana ve GoogleNet ile 22 katmana çıkartılmıştır. GoogleNet mimarisinde kendisinden önce geliştirilen mimarilerle karşılaştırıldığında katman sayısının arttığı görülmektedir. Toplam 22 katman bulunmaktadır. Mimari oluşturulurken hesaplama gücünün etkinliğinin arttırılması üzerinde durulmuştur. Inception modül adını verildikleri bir yapıyla gerçekleştirilmiştir. Tam bağlantılı katman kullanılmamıştır içerisinde. Yine GoogleNet mimarisinin yansıda görülen detaylı olarak gösterilmektedir. Yani Inception version 1 olarak da geçiyor. Şekilden de anlaşılacağı üzere mimari öncelikle klasik CNN mimarilerine benzer katmanlarıyla başlamakta. Daha sonra başlangıç modüllerin birbirine ardına eklendiği katmanlar gelmekte ve son olarak sınıflandırmanın yapıldığı çıkış katmanı bulunmaktadır. Son olarak bahsedeceğim mimari ResNet toplamda 152 katmandan oluşan bir CNN mimarisidir. Katman sayısı kendisinden önce geliştirilmiş CNN mimarileriyle karşılaştırıldığında oldukça yüksektir. Mimaride yansıda görülen artık bağlantı yapısı kullanılmaktadır. Artık bağlantı yapısının oluşturulmasındaki ana sebep katman derinliğinin sebep olduğu ileri ve geri besleme performans azalışının önüne geçirilmektedir. Bu yapıyla katman girişi ve çıkışı arasındaki fark elde edilmeye, yani giriş verisinin uğramış olduğu değişim ortaya konulmaya çalışılmaktadır. Yansıda gösterilmektedir ResNet mimarisi. Basit olarak artık bağlantı noktalarının birbiri ardına eklenmesiyle oluşturulur. 34, 50, 101 ve 152 katmandan oluşan mimariler bulunmaktadır. CNN mimarisinin karşılaştırılması yine yansıda görülmektedir. İlgili referansları altta paylaştım. Hepsine bakabilirsiniz. Birazdan yine referansları da paylaşacağım. Yukarıda belirtilen ve yaygın olarak kullanılan CNN mimarilerinin karmaşıklıklarının ve performans seviyelerinin karşılaştırılmasıyla ilgili yapılmış olan bir çalışma sonucu yansıda gösterilmektedir. İlk tahmin doğruluk oranları karşılaştırmasında en iyi doğruluk oranının Inception V4 ile elde edildiği görülmektedir. Diğer taraftan VGG modelinin çok fazla işlem gücü ve hafızaya ihtiyacının olduğu, GoogleNet'in işlem gücü ve hafıza ihtiyacının az olmasına karşılık doğruluk oranlarının yüksek olmasıyla etkin bir algoritma olduğu görülmektedir. ResNet'in hafıza ve işlemci gücünün diğer algoritmalarla karşılaştırıldığında orta, doğruluk oranının ise oldukça yüksek olduğu görülmektedir. Yansıda yine sol tarafta görüntü verisinin ileri besleme zamanları ve sağ tarafta güç tüketim değerleri yer almaktadır. İleri besleme zamanını VGG'nin en kötü, ResNet'in ise genel olarak en iyi performans sergilediği görülmektedir. Güç tüketim değerleri de incelendiğinde ResNet mimarisinin diğer mimarilere güç tüketiminin daha fazla olduğu, VGG mimarilerinin ise daha az güç tükettiği görülmektedir. Bizim yaptığımız çalışma kapsamında bilgisayarla görü alanında özellikle 5 yıl içerisinde yapılan çalışmalar incelenmiştir. Çevresel seslerin sınıflandırılması derin öğrenme kapsamında incelenen önemli konulardan biridir. Doğanın yapısı gereği sınıflandırılması zor olan bu seslerin spektrogram dönüşümü ve ön nitelik çıkarımı yoluyla tanımlamasına yönelik çalışmalar son zamanlarda hız kazanmıştır. 8. ve 9. numarayla, referans numarasıyla gördüğümüz yayınlarda yapılan çalışmalar incelendiğinde CNN tabanlı geliştirilen yöntemlerin başarım oranlarının oldukça yüksek olduğu görülmektedir. En sağ sütunda da kullanılan yöntemleri inceleyebilirsiniz. Bilindiği üzere CNN'lerin eğitim için oluşturulan veri setleri günlük yaşantımıza karşımıza çıkan doğal nesne görüntülerinin bir araya getirilmesiyle oluşturulmuştur. Her ne kadar CNN'lerin doğal görüntülerdeki başarısı ortaya konulmuş olsa da çizgi film gibi doğal olmayan görüntüler üzerinde herhangi bir test ve deneme yapılmamıştır. Doğal olmayan görüntülerde öz niteliklerin daha az olabileceği ve sonuç olarak bu durumun nesne tanımaya zorlaştırabileceği düşüncesiyle hareketle Yanagisawa ve arkadaşları 10 referans numarasıyla 2018 yılında yaptıkları çalışmayla CNN'leri Japon çizgi filmi olan manga üzerinde denemeye karar vermişlerdir. Bu maksatla bölge tabanlı erişimsel sinir ağı, RCNN ve Single Shot Detector, SSD yöntemleri karşılaştırma olarak denenmiştir. Çalışma sonucunda RCNN'in belirgin kenarları olan nesneleri, Faster RCNN'in belirgin olmayan kenarları olan nesneleri tespit etmede başarılı olduğu, buna karşılık SSD'nin nesne tespiti konusunda oldukça yetersiz kaldığı görülmektedir. Yine 11. Çalışmaya, 11 referans numaralı çalışmaya baktığımız zaman tünel ve köprü gibi yapılarda olası büyük çaplı hasarları önlemek için düzenli olarak denetim yapılmalıdır. Beton yapı üzerinde meydana gelen çatlaklar bozulmanın en erken belirtilerinden biridir. Bu çatlak tespitiyle ilgili bir çalışma yapılmış. ResNet 50, 101 ve Mask RCNN yöntemi kullanılmıştır. Sistemin eğitimini kendi oluşturdukları veri tabanı yardımıyla sağlamışlardır. 12 ve 13. referans numarayla yüz ifadelerinin tanınması, robotik, eğitim, pazarlama ve güvenlik gibi birçok alanda önemli bir rol oynamaktadır. Yüz ifadelerinin tanınması. Yüz ifadelerinin tanınması maksadıyla yüzlerce algoritma geliştirmiştir ve geliştirmeye devam edilmektedir. CNN'lerin popüler hale gelmesiyle çalışmalar bu yönde hız kazanmıştır. 12 ve 13'te yapılan çalışmalarda yüz tanıma maksadıyla çeşitli CNN algoritma denenmiş ve 190'ın üzerinde başarı elde edilmiştir. Sağlık alanında yine kara destek maksadıyla CNN'ler geliştirmektedir. Beyin MR görüntüsünün Alzheimer hastalığını tanıma 14 referans numarasıyla, akciğer görüntüsü üzerinde anomali tespiti 15 ve spektral tanımlayıcılar kullanılarak solunum seslerinin sınıflandırılması gibi çalışmalarla önemli hastalıklar daha erken çalışmada tespit edilerek önlenmeye çalışılmaktadır hastalıklar. Yine 17. referans numarasıyla CNN'in işlemci gücü ihtiyacını karşılamak için Field Programmable Gate Array bulut entegrasyonu içeren bir mimari önerilmiştir. Oluşturulan deney ortamı Seifert'ten veri setiyle eğitilerek denemesi başarıyla gerçekleştirilmiştir. Yine alias karakter tanıma, günümüzde bankacılık, tarihi eserlerin dijitalleştirilerek işlenmesi, akıllı tahta uygulamaları, otomatik çeviri gibi uygulamalarda sıklıkla kullanılmakta. Konu üzerinde önemli araştırmalar yapılmaktadır. Konu üzerinde çalışılmak için ilgili dile ait eğitim veri setinin olmaması önemli problemlerden biridir. Özellikle Türkçe'de böyle bir veri seti yok. 18. referans numarasıyla 2016 yılında kendi oluşturdukları Arapça eğitim seti ve CNN modeli yardımıyla %95.7 gibi yüksek doğruluk oranı elde edilmiştir. 19 Dalov ve arkadaşları 2019 yılında yaptıkları çalışmada günlük yaşantımız esnasında karşımıza çıkabilecek trafik işaretleri, reklam tabası ve benzeri ResNet 20 ve tasarladıkları CNN yapılarını Adboost algoritması ile birleştirerek tanımaya çalışmışlardır. ResNet 20 ile genel CNN ile özel niteliklerin çıkarılması üzerine durulmuştur. Sonuçta yine %98 gibi yüksek bir başarı elde edilmiştir. Yine akıllı görüntüleme sistemleri güvenlik başta olmak üzere spor, üretim ve otonom araç ve benzeri pek çok alanda yaygın olarak kullanılmaktadır. Otonom araç geliştirmesi kapsamında yaya ve araç tespitine yönelik CNN algoritmalarının başarı oranının yine 20. referans numarasıyla yapılan çalışmada karşılaştırılmıştır. Çalışmadaki tip ve Stickscape veri setleri Inception ResNet 2, ResNet 101, MobileNet 1 and 2 algoritmalarının eğitiminde kullanılmıştır. En yüksek başarı oranının Inception ResNet 2 ile elde edildiği tespit edilmiştir. Pardon. Sahil bölgeleri yasa dışı göç ve petrol sızıntıları, kaçakçılık, yasa dışı balıkçılık ve korsanlık gibi maksatlarla kullanılma riski yüksek bölgeler olup gerekli bilgilerin toplanması için bu alanların izlenmesi gerekmektedir. Yine 21 ve 22'de yapılan çalışmalarla az önce arkadaşımız da bir sunum yapmıştı. Uydu görüntülerinden gemi tespiti maksadıyla CNN tabanlı yöntemler geliştirilerek başarılı test edilmiştir. İncelenen çalışmaların karşılaştırılmasında bilgisayarla görü günümüzde pek çok kullanım alanına sahip, az önce de bahsettiğim ve yaygın olarak araştırılan bir konudur. Yapılan çalışmalar ile nesne tanım alanında gelinen noktanın insandan daha iyi bir başarı elde edilmesi sağlanmıştır. İncelenen çalışmalarda çoğunlukla VGG, GoogleNet ve ResNet mimarileri veya bu mimarilerin daha eski versiyonları ya karşılaştırma maksadıyla olduğu gibi ya da üzerinde çeşitli düzenlemeler yapılarak kullanılmaktadır. Genel olarak bu üç mimari. Belli bir konu üzerinde odaklanılmadı. Daha önce belirttiğim pek çok alanda farklı CNN ve mimarilerin geliştirilmesine yönelik araştırma yapıldığı görülmüştür. Derin öğrenme mimarisi etkin olarak kullanılmasına rağmen hala bir nevi kara kutu niteliği taşımaktadır. Öğrenmenin ne şekilde gerçekleştiği tam olarak belirlenebilmiş değildir. Hiperparametrelerin fazlalığı öğrenme başarısına etkisi çok fazla olup belli bir metodoloji geliştirebilmiş değildir. Hiperparametreler daha çok eldeki veri seti niteliği, yapılan araştırmanın özelliğine, yani tanınacak nesnenin türüne ve kullanılması planlı CRN yöntemine göre daha çok deneme yanılma yoluyla belirlenmektedir. İleride yapılacak çalışmalarda donanım ve yazılımla elde edilecek gelişmelere paralel olarak daha kısa çıkış süresine sahip, daha yüksek doğruluk seviyeli sonuçlar elde edebileceği değerlendirilmektedir. Bunlar benim kaynaklarım. Beni dinlediğiniz için teşekkür ederim. Sorularınız varsa alabilirim.
Thank you for your presentation. Dear participants, do you have any question the paper?
In English or in Turkish?
You can decide. It's up to you.
Okay, I have a question. As far as I understood, until now, the CNN training is being done in GPU's architecture. But you said the FPGA can be used for training or inference, right?
Yes, it was only a specific research for that specific paper. I am not trying to say that it is widely used. They were just try to speed up detection in one of the specific study.
Okay.
But it's mainly used in GPUs.
Okay. So we can use FPGA only for inference.
Yes.
Okay. Thanks.
Thank you.
Okay. Is there any question? Okay, no question. Thank you again. I wish you success,
Thank you, sir.
Mr. Feritcan. Mr. Sadat Duraki, are you ready to present?
Yeah.
Okay, if you want, you can start your present.
Can you see my? Sir, can you hear me? Can you see my presentation?
Yes, yes.
Okay then. Hello everyone. My name is Sadat Duraki, and I'm done this work together with my professor Selçuk Aslan and Sercan Demirci. I'm doing my master's degree on 19 Mayıs University at Computer Engineering Department. So the title of our work is Performance Analysis of Immune Plasma Algorithm with different donor and receiver configurations. So let's start. So first, in real world, we have a complex problems, engineering data problems that requires finding optimal values. So in most time, these problems have 1,000, even 100 of 1,000 decision parameters. So using like analytical methods that conventional analytical methods has some drawbacks, like gradient derivative based calculation for determining the search direction, also like high calculation cost, and also if the final solution changes dramatically with the chosen starting point, the algorithms redirect a lot of resources. So as a solution for these, we're using like optimization meta heuristics algorithms for optimization. What are meta heuristic algorithms? It tries to model a natural phenomenon and it applies its model for the solving the optimization problem. Until now, there is a large number of meta heuristic algorithms, which brings question: do we need more new algorithms? But if we take a look at the new free lunch theorem, it states that there is no single optimization algorithm, meta heuristic, that can provide the best solution for the all given problems. So there will always be a need for the new optimization algorithms. There we have like immune plasma algorithm. So immune plasma algorithm is a model that's models the steps of the medical method called convalescent plasma or immune plasma treatment. And in this work, we were modeling this medical method and implementing to solve the optimization problems. In this paper, IPA, as shortly for immune plasma algorithm, is used to solve 5 well-known benchmark optimization problems, and it's also compared with other state-of-the-art optimization problems. And the results are show that in most cases, the API has a better final solution compared to the other algorithms. So let's now take a look at general concept of the API algorithm. So at this picture, we can see the general concept is depicted. First, we have some infection. So infection is distributed between the individuals. After, I don't know, okay. After these individuals get infected, each of these individuals has some immune response to the infection. So depending on the immune response, we are determining the donors and the receivers. So the person with the best immune response becomes the donor, and the worst immune response, they becoming receivers. So we are taking the immune plasma from the donors and we are transferring to the receivers. So we can repeat this treatment, and we can even have a different number of donors and receivers. Let's now see the main processes that we have in the immune plasma algorithm. As I show in the picture, first we have like population initialization. So there is some population that has to be infected, and also after that using as donor and receivers. So the next one is spread of infection and the immune response. After that, we have the selection of donor and receivers individuals, and plasma transfer and donor update, because after some time, the receiver of the plasma has the better immune response of the donor itself. So we have to update the donor to find the better donor for our receiver, or this receiver now can become donor himself. For the population initialization, we are using this equation. We have xj minimum and maximum are the boundaries of our problem, and the random 0, 1 is the randomly generated number between 0 and 1. And for each parameter of the individual in the population, we are using this equation to find the parameter for each individual. The next process is spread of infection and immune response, and it is using this formula. In this formula, we are using as well random -1, -1 and 1, and also like a person who is infected, and we are choosing the infected person and not infected person. So we are spreading the infection. XMJ is infected person, XKJ is yet to be infected person. So using this formula, we are spreading the infection between the population individuals. So after that, after we have infection, we calculate the fitness value for each individuals. For those we have immune response for each individual, and when we get the immune response per individual, we can determine who's amongst these individuals becomes donor and receivers. So as I said, best immune response, individual with best immune response becomes donor, and with the worst becomes receivers. So how is plasma transfer done? We are using this process for plasma transferring. So on the left side of the equation, it's the plasma receiver, and we have donor who has the best individual best immune response, and we are transferring some parameters from donor to the receiver, and after that we are checking if the immune response of the receiver improved. If it improved, we can continue with the plasma transferring. If not, we can continue with trying different donors. And donor update, as I said earlier, if some receiver gets the better results of the donor itself, so there are individuals now have the better immune response on the donor itself, we have to update the donor itself. So we are using this equation for updating the donor. When you take a look at solving high dimensional problems, as I said earlier, nowadays we are dealing with complex systems, and we are using these meta-heuristic algorithms for solving these problems. But most of these meta-heuristic algorithms are not examined. Their performance is not tested in the high dimensional problems. Mostly they are tested till 30 dimensions. So in this study, we wanted to test the performance on API with some well-known benchmark optimization problem with 100 dimensions. Also, it's known that the performance of some algorithms tends to decrease as a number of variable increases. So this is also one of the reasons why we need to develop new algorithms. So let's take a look at our experimental parameters and experimental results. First, we have like total population size is set to 30. Maximum function evaluation number is set to 150,000. A number of parameters dimension is set to 100. This is set because we want to make comparable results with other meta-heuristics. So when we do the comparison in table, we have the same parameters for each algorithm. And these values are constant and are not changed during the experiment. The tested functions, we have square, quartic, Rastrigan, Ackley, and Gray-Rank functions. And also for all of these functions, we are finding the minimum. So the minimum for each of these functions was 0, as you can see on the right row. So now immune plasma algorithms can have configurations with different number of receivers and donors, and you can set the number of donors and receivers by yourself. How much do you want to have? And we have 7 different combinations. We tested with 7 different combinations where a number of donor receivers starting from 1 to 7. And for each of these cases, we run 30 independent runs, and those for the single optimization problem. In total, 150 independent runs are performed. So for each of these runs, we recorded the best overall best result, and also a standard and mean deviation of the function. So in this table, we are showing the results of API that's done with different number of receivers and donors parameters, value for the 100-dimensional problems. So the best results are bolded in these tables, so we can see that for the most cases, when the number of receivers and donors are set to 5, we obtain the best result in terms of mean and standard deviation, and also the overall best value. Only in some cases we have some different results, but the overall best value is mostly found when we set the donor and receivers equal to 5. So now, if you take a look and compare with other meta-heuristics, we can see that API outperforms the other algorithms with these compared algorithms. Only in the quartic function, we have this better standard deviation in the GVO, and also for the mean and standard deviation in function number 4. But the overall best value it's been found with API. So if we conclude what's done in this paper, we were studying the performance of the API that solves high-dimensional problems. Also, different problems and results of API were compared with state-of-art meta-heuristics. Results showed that finding optimal number of donor receiver is important, as we saw that when we use like 4 and 5 for the donor and receiver numbers, we get the best values. So with the optimal number of donors and receivers, it outperforms all the 5 algorithms in finding the overall best objective function value. So thank you for listening. If you have any question, I'll be happy to answer.
Thank you for your presentation. Okay, no question.
Okay, then I will.
Thank you
stop
again. I wish you
sharing.
success.
Thank you very much. Have a nice day.
Mr. Güner Tatar, are you ready to present?
Yes, I'm ready. Thank you.
You can start.
Let me share my screen.
Okay.
So, can you see my screen and can you hear me?
Yes.
Okay. First of all, I would like to tell my topics. I think it's my topics is not convenient here, but the community has deemed it appropriate. So we will continue from here. And my presentation topic is FPGA design of a high resolution FIR bandpass filter by using LabVIEW environment. And my name is Güner Tatar, and I'm a PhD student at the same time a research assistant at Fatih Sultan Mehmet Vakıf University in Istanbul. My supervisor, Salih Bayar, and my co-supervisor, İhsan Çiçek, are given respectively. So let's get started with the contents, and I'm going to give some information about the project with the introduction section, and finally I give some recommendation, and we will finish the conclusion. So when we take a look at the introduction, actually, what have we done? We examine high frequency resolution FIR bandpass filter design as a sample design scenario to compare a digital filter design flow based on traditional hardware description language, which means the VHDL, with the high-level design approach, such as LabVIEW. Of course, the designer can use another high-level language, C, C++, or Java, and another language. So we choose the VHDL, and this is the well-known hardware description language. So we designed the filter with the KZR window method with the about 18 kilohertz sampling frequency, and the 1.8 kilohertz low cutoff frequency, and 3.6 kilohertz the high cutoff frequency. Actually, we use the Harris rule of thumb method for filter design in terms of quick and convenient estimation. Of course, another ways to design this project, but we choose the Harris rule. And this is basic rule provide us opportunity to obtain information about the number of taps. Some resources tell that the taps means the order, filter order, for example, and during filter design and perform it with the iteration method. And the taps stands for here the coefficient delay or coefficient pair, and BT is normalized transition band. I placed here, and the 22 value is a constant given from the formula. I forgot to give in here the 50 dB is stop band attenuation, and I used the FFT fast Fourier transform to define the magnitude values of the signal. Actually, I gave the figure 2 the block diagram of FIR filter. Unlike the IIR filter, FIR filter doesn't have a feedback value, and it's only consists of 0 points. It's not has 0 or complex point, but it's only consists of 0 points in the complex Z plane. And we use the sampling frequency I said before, the 18 kilohertz it's about, and the low cutoff frequency I give, and the 50 dB stop band attenuation. So when we as we come to design of the high frequency resolution FIR bandpass filter, we use 24 taps, means 24 order of the filter. And this is the algorithm flowchart we use in the LabVIEW and the VHDL program. As everybody knows, the program program begins with the start, and you can initialize the filter parameters first, and then you can use another for loop or while loop to calculate the filter coefficient in terms of cosine values here and low frequency and sampling frequency, plus cosine high frequency, high cutoff frequency and sampling frequency. If the 24 order you obtain, then the algorithm finish, and you have the update error values, the last section of the algorithm. And when we come to LabVIEW verification of FIR bandpass filter, we perform both simulation and verification of the filter using the National Instrument LabVIEW platform. Here we obtain the coefficient of the filter from the filter that we designed graphically. And to get the coefficient, we used the sum of two signals. I gave here 2.4 kilohertz and 4.2 kilohertz as the test signal, and with the sampling frequency, we prefer the 90 degrees as the phase difference of the two signals with the amplitudes 0.8 volts and the 1.2 volts. We calculate the frequency spectrum of the filter signal using FFT, means the fast Fourier transform here. FFT is an algorithm where mathematical operations are done very quickly. While calculating spectrum of the signal, it's used a discrete Fourier transform, DFT, are used in the LabVIEW program. And we cannot use in VHDL program because it takes too long. Just take the values of the FIR bandpass filter parameters. We use the LabVIEW, and we use LabVIEW another way to get the simulation result. And the computing DFT for an application with the N data requires approximately N square, complex and time-consuming mathematical process. For this reason, instead of directly applying DFT for an application with N data samples, we prefer to use the built FFT algorithm provided by the LabVIEW. This is the zero pole location in the complex Z plane. As I mentioned before, 0 points are only given in the FIR filters. The poles doesn't exist in the FIR filters because it hasn't any feedback value. And this is the magnitude response and phase response of the filters. It takes from we took this figure from the LabVIEW. We see that the magnitude response only passes between this point and this point signals value, and the phase response gives us the which phase we have in the LabVIEW environment. And I gave the FFT transform simulation results here. The fast Fourier transforms gives us the information about the amplitude points of the signals with the test signals and the output signals. That means filtered and non-filtered signals. And the filter coefficient I tried to give here, and I use this coefficient in the VHDL program. I used the LabVIEW to take the filter coefficient because we didn't try to take this filter coefficient by using VHDL because it's very difficult and time consuming. So we choose the LabVIEW. And the LabVIEW simulation results gives that which signals suppress and passes the or designing filters. So this is the input signals that which is the sum of two signals, and the filter signals because we choose the 2.4 kilohertz signal to pass the filter. we verified these signals with the VHDL simulation results, and we see that the simulation results and real-time implementation results gives us the same value. And yes, this is the VHDL implementation top-level module diagram. I just try to give only one block here because, of course, there are too many entity, process, and other sub-programs in the program, but I just only give the one code block. This is the essential for us for defining the clock reset signal and signal in, which is sum of two signals, and the filtered signals, 2.4 kilohertz signal. And the algorithmic flowchart of the FIR filter design, like in the flowchart, we see that we first of all we initialize the filter parameters, and then we define the clock frequency and array size. The array size, according to your and depends on your taps or degree value. We defined it is 24, and first we compute the filter coefficients in the LabVIEW, then we use in the VHDL algorithm, and then these values can be updated with the for loop in terms of the iteration parameters, and then if we obtain the actual value, then stop the algorithm working. And this is the VHDL simulation results. It's like the same as the LabVIEW simulation results. If you take a look, the filter signals magnitude value is 0.8 volts, and the sum of two signals 1.2 volts. When we come back to LabVIEW simulation result, we see that filter signals has it's about 0.8 volts. So our project works well. So we gave the LabVIEW estimated FPGA resource utilization. We see that the LabVIEW use more resource than the FPGA platform, and I try to give some information about the LabVIEW parameters, function generators, FFT, FIR filter, VI is given in the LabVIEW parameters, and the other remaining usage. So this is the flip-flop lookup table, RAM blocks, multiplexer, and the signal processing, which are we used in the LabVIEW. And as a conclusion, actually FIR filters is graphical programming that is almost no chance of iteration for each piece of code. We see that the easy of use in LabVIEW, and there is no need to use the fixed or floating point implementation than the VHDL. If you use the very high speed integrated circuit description language, you need to use the double number turns the fixed or floating point value. If you want to use, for example, 1.312, you need to change this value to fixed or floating point. And we see that the LabVIEW is LabVIEW is not a human readable, and you can check all values of the program when you use the VHDL, but LabVIEW doesn't allow us. And the resource utilization VHDL is advantage of this platform. And the program size, when you use the LabVIEW, it takes a large program size, and if you use the VHDL, you can do your job only 3 or 4 labels, programs, steps. But if you use the LabVIEW program, it takes a large value of the screen, and the VHDL is suitable to take control the every point of the code, but the lab view doesn't give any doesn't allows us to control the code below. So this is the as a conclusion of our presentation. It was a quick presentation. It's the finally. Is there any question I can answer? Thanks for your listening.
Thank you for your presentation. Dear Parsim, do you have any question about the article? You can ask Mr. Güner Tatar. Okay, no question. Thank you again. I wish you success in your career.
Thank you.
Mr. Güner Tatar. Dear Elia Jebel, are you present?
Yes, I'm ready. Can you hear me?
Okay. Yes, you
Okay,
can start your
let me share my
presentation.
screen.
Okay.
Okay. Is my screen visible now?
Yes.
Okay, good. So allow me to introduce myself first. My name is Eli Shibel. I am a master's student in Bashir University from the Mechatronics Engineering Department. On behalf of myself and my co-authors, Dr. Bora Büyüksaraç, and my academic advisor, Dr. Burcu Tunç, I would like to present the study entitled The Effect of Number of Postures on the Accuracy of Center of Mass Estimation via SSC method. This is a quick summary of the content of this presentation. We're going to start by introducing the center of mass. So what is the center of mass? It is the point where the concentrated mass of any real object can be represented. So why are we interested in knowing this exact point? In our fields of studies, such as mechatronics or biomedical engineering, the center of mass is considered as an essential parameter. Like, for example, in humanoid robot systems, estimating the center of mass provides an important aid in the control of static balance and posture, as well as for human beings. The stability of human motion during standing and walking is highly influenced by the position of the individual's center of mass. Also, it plays a leading role in physical therapy as well. So when investigating a subject's capability to maintain balanced center of mass trajectory needs to be also known. Also, for the physical therapist, it also helps them with selecting the suitable training programs, as well as with the evaluation of the therapist's progress. So how do you find the specific point? Like for bodies which have fixed and known geometric shapes and made from single types of material, the center of mass will always coincide with the geometric center of this body, like shown in the figure above on the left. So like shapes like circles, cylinders, it always can be computed geometrically. For systems that are formed by an assembly of multiple bodies, the center of mass location is calculated as the weighted sum of the position of each segment center of mass. Like if you can see on the right, there's a simple example with two masses. If we know the center of mass of each object, we can multiply its mass by its position of center of mass, and we can combine them, and we can divide by the total mass of the system. This way we can get the position of the center of mass. So now we move to the most important thing, is estimating the center of mass in a complicated structure like the human body. The earliest work related to center of mass estimation predates back to the 17th century and is attributed to the Italian physiologist Giovanni Alfonso Borelli, who is also considered the father of biomechanics. In Borelli's study, what he did is he placed his subjects on a wooden platform and had a support shaped like a triangle, as seen in the figure below to the left. So to locate the center of mass, he kept moving the wooden platform until he reached a state of equilibrium. In this state, the center of mass is located on the line of contact between the support and the wooden platform. This was the emergence of the center of mass studies. Now, during our modern era of technology, using electronic equipment, a variety of methods are being adapted to estimate this particular point in both dynamic and static conditions. Most commonly used methods nowadays are force measurements methods. They require a force platform. These methods are considered the gold standard for center of mass estimations. And they usually rely on calculating the ground reaction forces and manipulating them using Newtonian equations so they can get the trajectory of the center of mass. Even though this technique is considered the gold standard, it also comes with some limitations because the use of forced platforms requires restriction of the area. So the subject has to always be standing on a forced platform to be able to estimate the center of mass, which is a huge setback for studies that need dynamic motion, for example. Also, there's another limitation, which is the cost of forced platforms. If someone was to do like a gate analysis, they need to buy several forced platforms and align them in order to conduct a study, which is very costly. Now, moving to the other common methods, like the segmented analysis method, this one requires a motion capture device that captures the position and orientation of the body segments. Usually in these studies, they determine the segment parameters relying on the data taken from studies done on cadavers. Usually these studies were published in the last century, but however, it is still widely used, but it is sometimes very problematic because when applying this method on different ethnic groups, the error rates goes higher because the studies were carried on specific types of population. So also applying this on atypical body types like maybe obese people or elderly people also generates a lot of errors. Now moving to the main aim of our study, which is to focus on the statically equivalent series chain, which is a really interesting technique to estimate the center of mass. This technique was due to the limitation of the previous estimation methods. Cotton and his colleagues in 2008, they proposed this new technique called statically equivalent serial chain, based on the work which was done on robotics in 1998 by Sesc and Bullitt. The main advantage of using this method is eliminating the necessity to know the entrometric parameters of the system under study. So instead of the equivalent values of the parameters are computed during an identification phase. So once these parameters are identified, only the joint angles are needed to estimate the center of mass, which is a really, really good advantage because if you only need the joint angles, you can just use any type of motion capture and just estimate the center of mass wherever you are. You don't have to be restricted in a laboratory environment. So the theoretical basis of SESC is the center of mass of branched chain system, such as the human body, can be represented by an equivalent virtual chain with the center of mass of the original system located at the end effector of this chain. I don't know if you can see it in the figure below. So the branch chain is like a really simplified figure of the human body, can be simplified by the chain on the right, which resembles like a serial chain. So for the mathematical modeling, I tried to keep this simple so I don't take a lot of time. For a simple example, like a 4-body system of articulated joints, the computation of the 3D center of mass is done using the following equation. It's a simple forward kinematics equation. And then it is reshaped until it looks like the equation below it, which resembles an equation of forward kinematics of a 4-link serial chain. So here we note the main interest of this approach, that the center of mass location of the original branch chain is modeled by the end effector location of an appropriately sized spatial serial chain. Now, since we said that this technique does not rely on anthropometric measurements, there have to be a way to find these parameters. So this is called the identification phase. So in this experimental phase, it needs to be carried out before the actual applying of SESC. And in this phase, we can find like an equivalent vector of values of the original anthropometric parameters. So during this phase, the center of pressure has to be recorded and is recorded as the horizontal projection of the center of mass during static postures, only static postures. To this purpose, the subject is asked to stand on the first platform and perform a number of static postures while his joints angles are being recorded by a motion capture system. After collecting the data, center of pressure and joint angle values are used to create a system of linear equations with the form like C = BV, where C is the vector containing the values of center of pressure, C of Px and Y, which is recorded by a force platform. B is the matrix containing the joint angles, and B is the subject-specific vector that contains the values which are equivalent to the original anthropometric parameters. From this equation, V is not yet discovered. So in order to identify it, there have to be a series of multiplications using linear algebra, and the more Penrose to the inverse is then used as follows. In this slide, we showed just a flowchart about the, like as a summary of the previous slide. So first we perform the postures and we record the joint angles and center of pressure. Then we identify the subject-specific vector, and later we can finally apply SESC to estimate the center of mass using only joint angles. Now, since SESC requires the capture of joint angles, we're going to speak about the motion capture systems, which is the focus of this study. So the majority of the studies which are using SESC tend to use optical motion capture devices, like shown in the figure above. These devices, however, always require specific experimental environment, thus eliminating one of the main advantages of using SESC, as we spoke before, which is estimating the center of mass outside laboratory environment. To this purpose, in the study, we present a comparison between the results of one of the first published studies by Cotton and his colleagues in 2009 that uses a cold standard optical motion capture system called Vicon Nexus. We used in the study a cheaper IMU, which is inertial measurement unit system, which is called XSense Awinda. So the main advantage of using an IMU-based motion capture system is the low cost, of course, and the ease of use and having an unrestricted experimental environment. Here you can see the difference between the setup of IMU versus optical, which is clear that the optical has some restrictions, while the IMU has the total freedom of movement. Now, for the experimental procedure of our study, the experiment was conducted in Bashir University's biomedical laboratory, and we used a young, fit and male volunteer who has been selected to participate. As for the force platform, which is shown also in this figure, we used the Bertec FT4060. And the subject, at first, before starting the experiment, was asked to put on the XSense Awinda system that consists of 17 inertial measurement units, and the sensor placement was done as instructed in the XSense user manual. Also, a calibration process needs to be conducted before we can start recording the data. So the subject was instructed to stand for 2.5 seconds in upright position called end pose, followed by a 16-second walk from and to the initial position. After completing successful calibration, the data recording of both devices was simultaneously triggered using a third-party module. So we can know, like, we can merge both center of pressure and joint angles data. Now, for the data pre-processing, a total of 51 postures were collected during the session. The recorded posture was deemed static only if the center of pressure deviation within a 200 millisecond window was smaller than 1 millimeter. Only in this case, the posture was deemed static. Also, a normalization of data was applied by matching a number of frames collected from the force platform and those of XSense using a spline interpolation in MATLAB. The center of pressure data later was also filtered using a fourth order Butterworth filter with 1000 Hertz sampling frequency and a 10 Hertz cutoff frequency. Now we move to the results part. In order to properly compare the use of both types of motion capture system, we followed what was done in the previous study. We took 19 postures out of 51 because in that study they only used 19 postures, and they selected randomly 14 of them to build the SESC model, and they used only 5 to determine the accuracy of their model. So here in this table, you can see our results, which was taken on SESC model using XSense. And also we can see on the right side of the table, the data of the center of mass taken by XSense, because XSense also has a built-in system that estimates the center of mass, but they use the segmental analysis method that we spoke about before. So in addition to the original comparison. So now we can see that the maximum error in our study was 16 millimeters, while and the previous study was only 12 millimeters, which is only 4 millimeters difference. As for Xsense, the maximum error was reached until 23 millimeters, which is really high. Also, to further evaluate the estimation ability of SESC in continuous motion, a swinging test along with a mediolateral axis was also performed. So the center of mass during this test was estimating using 3 different models. So the first model was built using 14 postures only, while the second one was built using 28, and the last model was built using 46 postures. And we renamed them SESC 14, 28, and 46. So the figure below shows the deviation difference between all 3 models for a total of 3,000 frames, which is equivalent of 50 seconds. It is obvious that the model with the lowest number of postures has the most fluctuation, which is SESC 14, while when we increase the number of postures, the fluctuation gets more tighter. Now, in order to verify that this is accurate, we compared it with the center of pressure data, and we also compared it with the Xsense data. So here also you can see that the SESC is really close to the center of pressure, with it's the actual position of the center of mass, while Xsense is always further from the actual value. So in conclusion, according to the results shown in the last 2 figures, SESC 46 appears to be having center of deviation close to Xsense and center of pressure, while SESC 14 appears to have more deviation. So in this sense, we can conclude that the increasing number of postures has a good effect on the estimation process. As for the results, during a static data collection, it shows that a low-cost motion capture device such as Xsense is capable of providing accurate outcome when it comes to SESC, center of mass estimation. However, in the built-in system of Xsense, it did not show a value of accuracy as SESC. This study was only a preliminary study, so it comes with some limitations, of course. One of the limitations is the low number of subjects. We only used 1 subject because also the other study only used 1 subject. Maybe future studies we will add more, of course. And also this study was only done on the mediolateral axis. We can also do it in 3-dimensional space, which we'll be also working on. And we can also change the complexity of the system of SESC, and we can test the accuracy depending on each model. And thank you for your listening. Are there any questions?
No, thank you.
Okay, thank you.
Sorry, I missed my volumes level. Thank you, dear Elia Jebel,
Thank you for having
for
me.
your presentation. Sorry. Dear Abdullah Ahmed, are you ready to present your presentation?
Yes, doctor.
Please, you can start.
Do you hear me?
Presentation.
Okay, thank you. Do you see my presentation, doctor?
Yes.
Okay, thank you. Hi, and welcome to International Symposium on Multidisciplinary Studies and Innovative Technologies. My topic talks about investigation of thermal modeling for underground cable ambiguity under different conditions of distance and depth. My name is Abdullah Ahmed El-Dulaimi, PhD student in Department of Electrical Electronics Engineering at Karabuk University. Outline, introduction, We'll talk about introduction, problem statements, study objectives, a geometric model of the cable, proposed model, mathematical model result, finite element method results, and finally conclusion. Introduction. Underground cables are affected by many different factors, including the temperature distribution surrounding the cable, the depth of cable, distance between the cables, the thermal resistivity of soil, and the materials which is cable is backfilled. The study and analysis of this factor are exploited as much possible to create the maximum possible current through the power transmission cable. The proposed study can determine the temperature distribution in the soil, backfill material, and around the cable. As we see in figure, the procedure of laying underground cables. Next slide, we talk about problem statement. When a high current passes, the temperature of the conductor increase. In the case of very high temperature, higher than steady state temperature, leads to a breakdown in the insulation of the power cable. This a failure occurs in the transmission line. The insulated material power cables begin overheads leads over 90 Celsius to excessive conductor temperature, which in turn cases in unsafe operation of the power transmission line. The soil properties in the area investigation of thermal modeling for underground cable ambacity under different condition of distance and depth change dramatically. So the study objectives talk about the simulation. Look at how the soil resistivity effect on the cable conductor temperature. A mathematical model was used to calculate the steady state rating current and finite element method for the thermal analysis, heat distribution around cable. Finally, keeping the cable within acceptable temperature limits. The geometric model of the cable. The underground cable used to experiment is of medium voltage, which is 33 kilovolt with a cross-section area 300 millimeters square. Figure 1 show the cable layers and diameters. Figure 2 show the temperature in contact with a soil surface and engineering calculation for laying the cable underground and the materials used for backfill the cable. So the proposed model. The proposed of heat dissipation and diffusion from the conductor to the surrounding soil affect the ambacity of the cable to create the current, and performance evaluation of underground cable system heavily influenced by this process. The heat transfer of underground cables is done by transferring heat from hot areas, the conductor, to cold areas, the surrounding soil and environment. Heat is generated in the cable inside the conductive material, but the insulating material prevents the heat diffusion, so the thermal resistivity is insulating materials resistance to heat flow. Here we see the proposed model. This flowchart represents an illustration of the proposed model for calculating the steady state rating current. We start with the rest parameters. We have n, the number of iteration, and I, the number of values for parameters. If the number of iteration bigger than the number of values, parameters values, we continue with the loop, calculate the thermal resistive of insulator, calculate the thermal resistive of the jacket, calculate the thermal resistive of soil and AC/DC electric resistive, calculate the electric loss, and finally calculate the steady state rating current. Finally, if we have the number of parameters value bigger than the number of iterations, so we save the underground cable rating and take it to finite element method. Actually, the others developed the finite element method to compatible with the mathematical model we proposed it. And left side, we see in the curves, regarding to curves, in left side, we see the mathematical model proposed calculation, and the right side is the finite element method others developed. The finite element method show that the heat distribution around the cables. Mathematical model result in this test, the space between the cables is 0.2 to 0.4 meters. Figure 1 shows that a relation between the relationship between the cable depth with underground cable rating current is inverse relation. In figure 2 shows the result of the relation between the resistivity of soil and underground cable rating current is an inverse relation. So the finite element method result, figure 1, as we see, show the temperature distribution around the cable, wherein in this case the soil depth is 0.8 meters, distance between cables 0.2, the soil thermal resistivity 0.8 to 1 Kelvin meters by watt, and the CSB resistivity is 1 Kelvin meter by watt. The temperature distribution indicates that the conductor temperature is more than 10 Celsius from the desired target, which is 90 Celsius. The temperature of the conductor should not exist than 90 Celsius. The material, the insulated material power cable begin overheads lets over 90 Celsius excessive conductor temperature, which in turn leads to unsafe operation of the power transmission line. Conclusion were made for single power cables with the flat configuration at period depth 0.8 and 1 meter, so resistivity 0.8 and 1 Kelvin meter by watt. Distance between the cable 0.2 and 0.4 meters. Two types of backfill material: cement, sand, mixture backfill, and thermal backfill for an aluminum conductor. The steady state rating is calculated using the proposed model and then investigated using a finite element method. Actually, the more explanation or details in the paper regarding to tables, equation, and more results. Thank you for listening.
Thank you for your presentation. Dear participant, do you have any question about the article? Okay, no question. Dear participants, dear Elnaz Pasha tried sharing her presentation full screen twice, but it didn't work. Now she will try again with a different method. Now she wants to present quickly her study again.
Thank you for much. Thank you so much for giving them again a chance for me. I apologize. Now, can you see my presentation?
Yes.
Yes, okay. Yeah, okay, thank you very much. So my name is Elham Pashai, and the title of my paper is Medical Image Enhancement using Guided Filtering and Chaotic Inertia-Based Black Hole Algorithm. So we have a brief explanation in introduction. Then I explain about the objectives of this paper, and where we use the image enhancement. I explain about our proposed method. At the last, we have experimental result and conclusion. So first, I want to explain about what is image enhancement. Image enhancement is basically the method of manipulating or improving the image, where the visual appearance of the output image is more compatible than the original image for a specific or dynamic application. So we have two different techniques for image enhancement. One of them is a spatial domain enhancement. Another one is a frequency domain enhancement. So the difference between them is that a spatial domain deals with the image plan itself, whereas the frequency domain deals with the rate of the pixel change. So here in our work, we use a spatial domain. Now, as in the introduction, I want to briefly explain about our proposed approaches, which is the chaotic inertia-based black hole algorithm. So what is a black hole algorithm? Black hole algorithm is an evolutionary algorithm and works with the stars. At the first, we create these stars randomly and put it in the search space at the beginning. So the algorithm then look for the best star, which called the black hole, using the appropriate fitness function. So after indicating the candidate black hole, star begin to travel around it, and the black hole absorb the star that fall into it. So during the process of the searching for the optimal solution, if a star reaches a better location while moving toward the black hole, the position of the black hole is changed with the star's position, and the search will continue. Moreover, if a certain boundary around the black hole, known as a event horizon, is crossed by a star during the movement, the black hole swallows the star, which leads to the birth of a new star randomly. Above the chart is a schema that has three critical characteristics. One of them is the ergodicity, another one is the stochasticity and sensitivity to the initial condition. The combination of these properties guarantee the diversity of the solution began and therefore improve the performance of the evolutionary algorithm. So the inertia weight is a coefficient that controls the balance between the exploration and exploitation. So chaotic inertia weight is exploited to efficiency control the convergence of to the best global solution. So guided filter, I want to explain a little about the guided filter. Guided filter is a technique that preserve age and details of the image while removing noise and also avoid straight graph and gradient reversal artifacts on the resulting image. In order to smooth the input image, the guided filter use the content of the input image and the guiding image. But the objective of the paper is to make an image more suitable than the original image. We try to enhance the contrast, but keep the natural looking image, and to make this image suitable for the dynamic field. So as you know, image enhancement can be used in different applications. For example, medical sector, remote sensing application, documented image. Here, we in our paper, we apply this, our proposed approach of medical images. So at the proposed approach, as you can see from this figure, at the first we have an input image, then we use a guided filter. In fact, we apply the age preserving smoothing filter method. Then we reach the smooth output, and at this smooth output, we apply our chaotic inertia weight black hole algorithm with the appropriate fitness function in order to give or reach the enhanced image. So our proposed fitness function is a combination of the two fitness functions. First fitness function is this, which can be calculated by this formula. Here, IE denotes the obtained image after transformation. ISC is the resulting image after performing the Subel age detection operator to IE, and EISE is the sum of the age pixel value. And the second fitness function is this Q multiply with 0.5 multiply with the HIE and logarithm 2 plus EISE multiplied via CE. So Q here is in universal image quality index, and HIE is a entropy of the image, and the N indicate the GLCM based energy, and the C, this last one, is a GLCM based contrast. So this is our proposed fitness function. Now we have an experimental result. At the experimental result, I compared the performance of two state-of-art fitness function with our proposed fitness function on only one medical image, and I compared the performance with I showed with the 6 evaluation metrics: contrast, H pixel, number of H pixel, entropy, PCNR, and SSC and MSC. As you can see, the performance of our proposed fitness function compared to other approaches in most of the metrics is better than these two state-of-art fitness function. So as an experimental result, I applied our proposed approach on 3 medical images. The first one is this, and I also showed a histogram of that, compared the performance of our proposed approach, the last one, with 10 state-of-art methods. One by one, I explain both of them, and there are the histogram. As you know, the best histogram is that they follow the original image, and it's a flatter. So our proposed approach is better than the others when you compare them. Again, for the second one, it's the chest image, and the histogram of that. Also, the performance of our proposed approach is better compared to other approaches, better than all of them. And for the mammography image, also, as you can see, the result of our proposed approach is acceptable. So now I show the performance of the proposed approach compared to these 10 state-of-art methods for entropy and PCN. We show with the 2 parameters criteria, and this is entropy and PCNR. Our proposed approach, when you consider the PCNR compared to other approaches, can reach to highest one, and in terms of the entropy, second highest one in most of the image. So at the conclusion, I can say that in this study, we propose a new hybrid approach, which can be applied for the medical image. The main idea is based on the hybrid of the guided filter and chaotic inertia weight black hole algorithm. In the proposed approach, we also propose a new objective function, and the experimental results are verified on medical image by comparing with the 10 well-known image enhancement technique in terms of the 2 criteria, entropy and PCNR measurement, and the extensive experiment along with the qualitative and quantitative evaluation show that the suggested method can successfully enhance image and perform better than most of the techniques. So as a future work, the usefulness of the proposed method can be investigated in solving a related domain of the image process, such as segmentation and noise reduction. Thank you very much. Thank you again for listening and give me another chance. Thank you so much.
Thank you for your presentation. Dear person, do you have any question this article? For this article? Okay, no question. I wish you success. Thank you again.
Thank you so much. Thank you.
I want to end the session. Dear participants, hope to see you at next session. Starting at 1:30. Have a good day.
Have a good day too. Thank you so much.
Thank you very much.